let's start.
Okay, so then I will. I think my camera will be off from now. I can turn the recording on just in case, so that we have two recordings, one from your side and one from mine. And so I'm very happy to be back. Thank you for the invitation. You see that now at this point I don't have even immigration in the title. So
Okay.
The plan has changed a little bit. I will tell you in some more detail things that probably today Vitaly might be bored because he learned it from me, but it will be kind of a reminder. And for the others, it's going to be some interesting things, I hope. And it is something that I last time when we met, so I spoke in the seminar. I answered two questions. Somebody asked a question about the arguments and how the proof was going. So that was one of the first questions. And then I gave a relatively long answer. And I think today I will go in more detail about a construction of the multiplicative coalescent. So let me know if there is a problem with something. I can move this off so it's not recorded, maybe. And so let me remind you that in words, we have a process. It is a merging, or rather pairwise merging of blocks. And if I have a block of size, or rather mass, so I have a block of mass X and a block of mass Y, and maybe many other blocks. I mean, I just put these inside configuration. So we have some special blocks, two blocks. So they will merge, they will coalesce, they will connect at rate at infinitesimal rate x times y, and this is the same for any pair of blocks simultaneously. There is a rate, there is an intensity, multiplicative intensity, multiplicative rate of merging. So I assume that you remember, or you looked at my previous talk, and then in the meantime Vitaly talked about our joint work, and so this also improved the understanding of the basic model, I bet. And please ask me if something will be unclear. Of course, just interrupt me. So today I'm just going to remind you here that, x in L2 decreasing means that x is an infinite vector, which could be finite, in fact. So we have coordinates, and they are ordered in the non-decreasing way, and then the L2 norm is finite, or the sum of the xi square is finite. And this is the state space, so the state space, natural state space of this process. In general, in fact, it lives on L2 without L1. Okay, because that's in general. But today we will actually still mostly think about finite starting points. So today we'll have x0 is some general x1, x2 up to xn, say, and then zeros. And I will explain a construction or a representation. So construction or representation, or you could say coupling. It is all of that of multiplicative coalescent, which is kind of restricted to this these states, and well, a couple of constructions, but related, and using them you can then go ahead and prove, for example, scaling limits that I told you about last time. So the original oldest theorem and its generalization. So these constructions were, they were improved by me some years ago, maybe 5-6 years ago. I understood that there is a better representation. Some original representations were used by Aldous 25 years ago, and then we reused them in my thesis and in my work with him. But I like the new, I think the new thing is really much more powerful and nicer. And so that's what I'm going to explain today. And so I don't know if you have any questions about this. This is the very beginning. It's a reminder of well, it's the summary. I wrote many pages last time, I think, and it's the summary of what happened. Many things were said also about random graphs, but now we jump to the multiplicative coalescent immediately. And so here you have a state space, but we will only consider finite state space states for now, and it's the process of merging, piling up. Okay. And so they merge. So when these two blocks merge, then this becomes a new block of mass x plus y. And okay, so it is a Markov chain or Markov process. Now I'm thinking of how I would, so there is this, there are two constructions, in fact, two related constructions. And it is about, so initially we have this x1, say x2, maybe they are ordered. There are these masses of blocks, or blocks of finite positive mass, okay, and xn, and they are all positive, and so others are not there, or we could imagine that there are infinitely many zeros following, and so we would like to somehow construct this, so it is maybe counterintuitive, but they will be, so I would like to represent this using a walk like structure, so that the connected components of the coalescent become, or rather their masses. So we, at some time, say time q, so I have coalescent time q, and so my coalescent is running until that time. So there are edges that start being built. I mean, some of the edges appear by time q, others don't. And I take a snapshot at time q, and I would like to represent the connected component masses. So this is indeed, the process of connected component masses under the multiplicative mechanism. That's the multiplicative coalescent. So this is say pi q is my vector of, so random vector And, you know, it should be, well, there are only finitely many positive terms, so this one is certainly positive, and then the rest is zeros, if you wish. So I would like to represent these as excursion lengths of something nice. And it turns out that there is a natural coupling, so what I need is a pool of independent exponential variables. So independent exponential, but they are not IID exponentials. So I have psi I, which is distributed as exponential rate xi for every I. If all the masses are the same, then they are indeed IID, but typically not all the masses will be the same. They don't need to be. I have this time, so Q is the coalescent time, and then there is this. Okay, so what I could do is well, let me then, you know, there is the process. I'll write the process, and then we will. Okay, consider the following stochastic process. Z x q, so q is the time and x is the initial vector of masses at time s. So s is some auxiliary time. And it is a sum. I goes from 1 to n. Xi indicator that xi is less or equal to s. Except it's not xi, it's xi over q less or equal to x. So this time, coalescent time comes in here, or I could write xi is less or equal to q times s, and then minus s. Or I could, it is the same, this would be the same as if I ordered, I did order statistics. So I have, so pi I, I'll tell you soon what it is. It's the natural thing. So here I have ordered statistics. I've ordered statistics of psi over q less or equal to s, and then minus s. Okay, it is the same process. So let's look at it. I mean, a diagram, a graph. So sum xi indicator xi less or equal to s minus s. Here's s, and so what it does, it is I have here ordered statistics of xi. So there is the first one, the second one, xi2, xi3, and so on. They keep going. Okay, s. Maybe this is xi k, and so on. So the process has drift 1, negative drift of size 1, so it just keeps going. And then at these times, jump times, it jumps by the amount of the, so, okay, so now it's time to say what pi I is. So it's sum x pi I indicator that xi ordered ith less or equal to s minus s. Of course, pi I is the index that goes with xi ordered I. So pi I is k if and only if psi I is psi k. Okay, you run these independent exponentials one after the other, and of course the first one, the smallest one, will have certain index, and therefore pi 1 will be that index. The second smallest one will have another index, and so on. And so the jump will be by this pi I. So here there is a jump, and this jump is say, okay, x, this jump is x pi 1. And the process keeps going always down, down by at rate 1. And this is this deterministic rate, so it's a slope minus 1. And then there is a new jump at time psi 2. There is a jump up of size x pi 2. And it keeps going like that. Okay. There is the third jump and so on, and keeps going like that. Okay. And there's only n jumps, and after that it just is a deterministic function. But these jumps are random, and okay, so it's a graph of that of something. And in fact, I could now do the coupled construction to that. I could construct. So sorry, I usually do this. So it's psi over q, and here I should have, write q. Okay, so psi 3 over q. I do this coupled construction because it depends. So this is a process that depends on x and q. Okay. Of course, these are deterministic things, and then it depends truly on size as random input data. Okay, so it turns out that this is a graph of something, but in fact, you can use the same data in this way to now couple it to the multiplicative coalescent pi of q. Okay, so at that time, started from x. Okay, and x is this vector x1 up to xn, and then 0 if you wish afterwards. Okay, so maybe I put this recenter, and so why and how would you go about that? Well, it is sort of like exploration process. So this initial time until nothing happens, it is, this is something that concerns only the process z. But as soon as this happens, it gives you information of where to start. So it's like an exploration process of connected components. So it starts with the block indexed by pi 1. And this block was chosen through the ordering of size. It's truly, the lowest variable, and this happens with the probability that we know well. The probability that pi 1 is some index, some specific index, is just, well, okay, let's write it. So probability that pi 1 is, say, L, is just XL divided by the sum of XI, 1 to n. That's the elementary properties of exponentials. So in that sense, the first block was chosen in size biased or mass biased way. And so once I do that, okay, so there is actually a line that I should draw in a different color. I'll try. So there is a line beneath, or, in parallel to this graph, there is a timeline here. And so what I do is at this time psi 1 over q, I indicate an interval, and it's exactly the same. So here it will be, here I'll indicate exactly x pi 1. At this time, I know what is pi 1. It is the index of the first psi, and here this is x pi 1. Okay. And during that time interval, I pretend that I listen to for the children. I listen for the neighbors of of the block x pi 1. Okay, so here's x pi 1, and here I now I'm just using this picture to draw you from here. I will draw a connections, so who is connected to what in sufficient manner, so certain won't matter, but I will know from here what are the connected components in here. I will find the state of pi. It will have the same distribution as pi of q. Okay, so that's the coupling. So now, okay, so up to here nothing happened. Now I know that I'm looking at x pi 1, and during the interval, next time interval of exactly this length, I'm listening for the neighbors, or for the children, if you wish. It will be like a tree for the children of x pi 1. And here's the jump that happens. So we look at the walk, blah, 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 and it jumps. Okay, so it jumps at a certain time psi 2, and of course at that time I know what is my pi 2, and there is another block here, x pi 2, and I say, okay, because this jump happened, and maybe some other also happens, but because it happened during this time, of this interval period of listening, I make this connection. Okay, and there may be others, but here there aren't any. Okay, after I'm done, I look at whoever I've seen. So psi 1 is gone, I mean pi 1 was explored, but there were children of pi 1, and or maybe not, but here there was at least one child or one neighbor connected by an edge, and that's x pi 2, and now I draw an interval of just next to that there is a period of time of size exactly x pi 2.
Is it like busy period in queuing theory?
Yes,
when you have arrivals and
yes, it's very much, yeah, it is something, it is not quite that, but yes, it resembles. For example, this is a load free time, and now you have a certain load. Okay, so you start with a load, but there is a, yeah, I mean, we do it with a different goal, and we'll achieve something like in a queuing theory. So let's wait until the end. You can maybe say what this reminds you of. But okay, so now this new interval is x pi 2, and now I'm listening. So it's like a service time. I mean, serving something, and so the purpose here is to find the neighbors of pi 2, or the block which has mass x pi 2, the block indexed by, so you see this block is indexed in fact by pi 1, this block is indexed by pi 2, so now I'm looking for neighbors of pi 2, and it turns out there is a jump of psi 3, so in fact there is psi order 3, and that's the block with size x pi 3, and there is this link, and this procedure keeps going. And what will happen is that, for example, here, let's imagine that, well, okay, let me draw another. It's not so important that all of them be, yeah, go ahead.
You have 2 children.
Yes, okay, let's try. Yeah, you can have as many as you wish. Sometimes, I mean, n at most n minus 1. But of course, there will be situations. So, for example, for a larger time or different configuration of size, there will be situations. So let me now redo this. So psi 3 of q over q, and maybe here is still psi 4 over q. And now we have a slightly different configuration where, for example, here's a jump. So the first jump is x pi 1. Here's another jump. Okay, so x pi 2, another, I hope that I fit 2, yeah, so they should be closer to each other, and then, okay, like that. Okay, so a bit different. And so if I say, so there is this same picture with listening times. So first nothing happens, and then starting from here, from this, well, you could maybe open from the left, and then I listen for the, let's pretend that this is x by 1. Okay, it's not quite corresponding to that, but so now I would have 2 children of x by 1. Okay, so I mean, of the block indexed by pi 1, somehow it would be connected to pi 2 and pi 3, and then here I would have x by 2, and during that interval there is nothing happening. So you see, so I see no other jumps than x by 3. Okay, and I see no jumps either. So this means it's detached. And what is very interesting, well, if I drew it, I didn't draw it exactly up to scale. Maybe if I do it like this, okay, maybe fudge here, cheat a little bit. So at the moment where I cannot add anything any longer, it seems that, you know, here's a tree or a connected graph. There is no cycles because always there are new edges, or rather edges with new vertices to explore. So I arrived to something, and it's interesting that this process Z, it started from here, and it went up by jumps. So how much did it jump? It jumped by x by 1. So everything that happened in between. So x by 1 plus x by 2. So total jump jumps upwards, where x by 1 plus x by 2 plus x by 3. And if there were some others, you know, plus, so in the picture there is no, okay, but there might have been others. And during that same amount of time, it always went down by 1. I mean, not by 1, but at rate 1. So during the time, it went down by 1, during the interval of time, which is exactly equal to the sum of all the jumps. So it is an excursion. It is an excursion above past minimum. I really started from here. There were certain amount of jumps, certain jumps that happened. Each of these denoted that I had to connect the block of that mass to some block, to whatever its parent is in the tree, and then during the same amount of time, the process was always going down, but at rate 1. So the amount it jumped up is the amount it came down. So exactly at this final point, it is at the same level. Okay.
I have one more question. It looks like a Skorokhod reflection problem. Is it, or it is not?
Well, I don't know. I don't know what you mean by Skorokhod. I mean, I know the reflection. Yeah, I'm not sure what. I don't think so. I don't think so. Yes, go ahead.
I think that it is related really to Skorokhod problem because there is a construct when we just organize a trip along the leaves of random tree and associate it with the excursion of the Brownian motion.
Yeah, sure.
Yes, and in this way it is related, yes, to reflected Brownian motion. But I think that you do this construction before the limit procedure. So
yes. The point is that it is a discrete. It is a totally discrete construction. Yes. That works. You know. So here, indeed, I have just a vector and finite vector, and there are zeros, and so there will be finitely many jumps. And so what's interesting, we can continue. So for example, here, there will be another load-free interval. I call them load-free because it's like in the excursion theory. I'm sorry, like queuing theory. And then at this time, okay, I just move this. Okay, ignore this. This is now, the next time, there is again going to be a size biased or mass biased pick from the rest of the population. So some things we've already discovered and we never touch them again, but now there will be a new component which will be chosen. So its first vertex to be discovered is x pi 4. And at this point, the jump will make the process will make another jump. Say this is x pi 4, and in the corresponding to what we did before, we just indicate an interval of size x pi 4 here, and then during that interval, we listen to whatever may come along. Maybe nothing comes along. Maybe there's no the next jump xi 5 over q is further down. In this case, this component is alone. Okay, we've explored it. It consists of only one vertex. If something else does come along, then it becomes during this interval. Then it becomes attached to here, and we keep going as we did with the previous, with the first component explored. And by the end, so this exploration process is finishing at the last, at psi n over q, we know everything. And maybe even earlier, depending on if psi we will know maybe earlier that this did not connect to the psi n minus 1 over q, then we don't have to explore after psi n minus 1 over q. But okay, at least by this time we are sure in all no matter what, depending on the configuration, omega by omega, we are always sure by this time how is this graph, or a forest. So we come up here with a forest, random forest. How is it constructed? And so my claim is that here we have excursions. So excursions above past infimum or past minimum of z, of the process z, they have mass, not mass, but length. So we have here an excursion, and it has exactly the length x pi 1 plus x pi 2 plus x pi 3, which is the mass of this. In here, we have just one node, one block. It has mass x pi 4, and the excursion was also very simple. I drew it wrongly. The excursion was this, right? It was just this triangle. First the jump, and then the triangle. Nothing happened during it, but it is the simplest such excursion. And again, it was excursion above past minimum. So this is the minimum, and its length corresponds to the mass of this very trivial. The very simple component of mass x pi 4, and then it will be the same. This procedure keeps going, and we will arrive to some other components, and so on. Okay, and every time we can match first excursion to the first explored component, second to the second, and so on. And the point is that these are the components. I mean, there may be some other edges actually also present, but we don't explore for them. But these are truly the components, the connected components of the multiplicative coalescent at time q. And the reason for that is, so I have to draw the picture again. So let's draw this picture again, at least the beginning. So you'll trust me for the for the continuation, so for the first excursion, okay, so something like that, xi1 over q, xi2 over q, and xi ordered 3 over q. Okay, suppose that it goes like this. Okay, xi4 ordered over q. So what is really happening? I have x pi 1, and then there is this listening time. Starts from here, but nothing happens earlier on. So there is this listening time, the first listening time, x pi 1. So what is the chance that actually something of size, so here I have x pi 2, I have something, okay? So at this point, I know that pi 1, so here, at this time, I know that it is indeed the block of mass x pi 1 that I'm, or rather the block indexed by pi 1 that I'm considering. This is my center of attention. And so whatever comes in during this interval of time, I will call a child, or, you know, connected to x pi 1. So what is the chance that some other L, so I take any L different from pi 1, and I ask for the probability that xi L over q, it enters inside of xi 1, not xi L, sorry, xi L, truly xi L, not ordered L. It enters inside of xi 1 over q, and xi, well, it won't be xi 1 over q, but xi 1 over q plus x pi 1. Okay, this is my interval. This is this interval of list. I mean, rather this time period that I'm listening for the yeah, and I can, you know, whatever, I can look at the filtration, or rather the sigma field available at time xi 1 over q. Okay, so conditionally on all the previous information, there is not much. I just know what happened in here. So what is the chance that I see xi L over q entering inside of this interval? Well, due to the independence, remember xi I are independent exponentials. Okay, so they're independent exponentials. So this chance is I have this conditioning here, but it really doesn't matter. There is a independence and memoryless property, and I basically have an interval of length x pi 1, and I'm asking what is the chance that an exponential random variable enters in that. And so this is 1 minus e to the minus q x L x pi 1. Okay, well, okay, so this is conditioning. I already know what pi 1 is. Okay, so and it is going to be the same for all L, and even it will be true. How do you say this? It will be true not in terms of marginals, but rather joint distribution. So I could consider two such xi L1, xi L2, and so on. So they are still independent. The point is they're independent, and given this, they will be conditionally independent. The probabilities of them doing this jointly will be the product of these probabilities. So I'm getting, you know, and this is precisely the chance of the block of, you know, index as pi 1 being connected to L in the multiplicative coalescent at time q, right? Because multiplicative coalescence, well, I'm running x pi 1, and here's xl, and so by time q, the chance that they are not connected is just exponential minus q xl times x by 1. It is the multiplicative rate, okay, multiplicative exponential, okay? So it is truly the multiplicative coalescent probability that they are connected. So these children that I children, or we call them children, they will appear in here in this listening procedure of Z, if and only if, or rather it is a coupling. So if they appear here, I can draw this, and it's truly like with probability, with multiplicative coalescent probability. So the edge is here with the probability e to the minus q xl x by 1, and another edge will be also, you know, some xk and so on. And you see, I don't need to worry about these extras because they might be here. There is no way how I could, with this information, with this data, only xi, once I use for each block only one xi. I have at my disposition only one xi per block. So in here I don't have information whether they connected, but I don't care. They are connected by a path through, for example, x by 1, or maybe here there will be another child that is connected to this via a longer path. And it is truly, you know, when you think about it, what is going on now, so the first connections during this time interval are according to the multiplicative coalescent rate. So then after this interval, I know that there is no one else connected, so I explored all the connections of x by 1. Those that did not happen, they did not happen with this probability, the probability of not being connected, okay? But maybe they are connected to someone else. So then I start exploring what is the situation with x by 2, okay? So x by 2, or rather the block indexed by pi 2, and again, it is going to be conditioned on everything that happened up to this time. There could be new connections from the blocks that I didn't see so far to the pi 2 block. There could be, and they happen. I decided they will happen if there is if there are jumps during this interval, and if there are for those jumps that don't happen, I leave them for later. So if provided there is a jump during this interval, I will attach them to x pi 2, and it is again with the multiplicative coalescent probability, because conditioned on everything that happened so far, I still have independent exponentials that did not yet happen. And there are these memory-less properties of exponentials that, you know, it is a slightly more complicated expression than here because there is more information in this sigma field. But still, I'm just asking whether a certain rescaled exponential, therefore exponential itself, has happened during a certain interval of time after an independent and another exponential that is independent from it. So all these rates will be multiplicative coalescent rates. Really, you know, they will be. They're truly recovering. So I'm recovering like a spanning tree. Sorry, I'm recovering a spanning tree of the multiplicative coalescent first component, and so I think this.
Hello, I don't hear anything anymore.
Vlada, your sound.
Yes, Vlada disappeared.
No, Vlada is here.
But not Vlada.
Oh, okay.
Vlada is here, but we don't hear her.
Mm-hmm. Maybe we have to write here. Mm-hmm. Mm-hmm.
I wrote her a message.
Okay, very good. Because I also began to write.
Okay, she's off now.
Mhm.
Okay, I'm back. I'm back. I hope you hear me. I'll put
Yes,
Yes.
yes.
Okay, there was a glitch in the internet. I'll just put the screen on again. Okay, so I don't know what was the last thing that you
You said that we can recover from this spanning tree from the process.
Yes, that basically it is the tree. So first tree is it's a spanning tree of the first connected component. Second tree will be the spanning tree of the second connected component, and these components are not, the algorithm chooses them via these size biasing. So basically, it is a random choice from which block we will start, and then we continue. Then after we explore everything that was connected to it, either directly or indirectly via other things, then at some point the excursion stops. I mean, it is the full excursion above past minimum. Then we wait a little bit longer, and then there is a new block, a new component, and it starts being explored from this block, and we keep going. So it is an interesting, I think, quite interesting construction or a coupling, a realization of multiplicative coalescence. So then all we need to do is add up all the masses and order them, and we will have our realization of pi of q. And here we have a walk. Oh, well, it's not quite a random walk, because you see, the problem is that these psi's get exhausted. So I have the first one and the second one and the third one, and after a while, I'm running out. So it's not like it's like a Levy process, but but only the first jump is saved. So for each rate you would have in principle many jumps, or maybe it's like a cumulative. What is it called? Cumulative jump, or I'm running out. So never mind. It would be a very simple Levy process if we took for each of these x's, you jump at a certain rate, you go down. But then these jumps would be infinitely many. Here we just keep one jump per rate. Okay, one jump per block. The first jump per block, but okay, it's some kind of a Levy-like process. And it turns out that its excursions above past infimum or past minima are precisely describing, so these excursion lengths are giving us the masses of the coalescent. And okay, so this is something interesting. And then there is another, so I discovered this not just by its, we use something similar, so all this came up with something similar, but more cumbersome 25 years ago, or more, 25, 26 years ago. And then I ran out, this is an invention which was actually, it came to me because of another thing that I wanted to understand, and it's somebody else that had this idea. So, the motivation for Z, okay, so motivation for this construction lies in something I called Uribe diagram for ZXQ, comes from Uribe. So this is Geronimo Uribe Bravo, Lieber's diagram, who in turn was explaining Armendarit's construction. Armendarit's construction of the multiplicative coalescent. And so here's the graph. So now we have a different graph, but we have the same input data. So we have X and Q, and we wonder how could we construct pi of Q. So pi of Q is again the multiplicative coalescent, and again X is just finitely many. So first n components, n blocks. First n have positive mass, the others don't exist, or have zero mass. Okay, we want to construct pi q, and we have the same. Well, we say that psi I is again exponential rate xi, and they are independent. The same input data, and now a different graph is as follows. So here's psi. So now I'm putting the psi's on the abscissa ordinata, on the ordinate axis. X1, psi1 is the first ordered, psi2, psi3, psi4, psi5. And then there are these lines. So there are line I, which has the formula y equals psi I, ordered I, minus, there is another time, well, let's call it Q. This time let's call it Q, because you see, in here, in this picture, S is auxiliary time, and it's not the coalescent time. The coalescent time is Q. And here, it's truly the coalescent time. So Y is Q, and it's Y, minus Q, okay, I, okay. Maybe I should first say what is the first line. L1 is Y is psi1. So nothing happens, it's just a constant. It doesn't have a slope. L2, Y is psi2 minus Q times X pi1. So I take, it is a negative slope of size X pi1, and pi1 is precisely what it was earlier on. Pi1 is equal to L if and only if psi1 is equal to psi L. So on the event, rather, on the event that psi1 is psi L, pi1 is L. These are the these are the same event. And so, so it's something like this, okay? It's a line, but I don't draw, okay, it should go further. L3 is similar, sorry, L3 is Y is psi ordered 3 minus Q times X pi 1 plus X pi 2. So the slope is changing. It is negative and bigger, larger negative. So it's something like that. Okay, and it intersects at some point. It intersects the previous line, and so on. Okay, so let me redraw it. Okay, so I hope you. Maybe I write here the formula for the line K. So it's Y is psi. Okay, sorry, should be moving this. Y is psi ordered K minus Q, and here's X pi 1 plus X pi 2 plus X pi K minus 1. So I always take all those block masses of all the indices that appeared previously in previous lines. I add them up together, and that's the new slope. So let's go again, psi1, psi2, psi3, psi4, and so it's like this, and maybe this, maybe that, maybe this, and so on. It's something, you know, looking like that. So the lines are deterministic. Well, they're random, but they're random only through their initial data. The initial point. So at time 0, each line starts from its psi ordered. And
also through the choice of x, the randomness comes also from the numbers p1, p2, I think, yeah?
Wait, yes, but they are known, yes, but they are kind of known once you, okay, so it's also the information,
yes,
you're right.
all information is covered in psi.
Yes. So
my remark was just that this lines is random from psi itself and also from these numbers which
you're right. You're right. Yeah. Okay. And now you notice that I stopped. Actually, I stopped drawing the lines after each line. At some point, will intersect with the lower line, and I stopped drawing them from that point. It is nicer this way, so I only draw them up to an intersection. And so here's a construction called Armendaritz construction, but this diagram was done by Uribe because he tried to, he made sense to me. I understood what Armendaritz construction was about from this diagram, so I call it Uribe's diagram. So here, in fact, what we do is it's like genealogy. So now it comes, before it was like hewing, and here's like, Moran model or some other model. So genealogical tree. Analog. Okay, so we pretend that we have a partition structure and that each line starts with each line represents a certain partition equivalence class. So initially, the partition at time 0 is the trivial partition where everybody is alone. Okay, and so it is from this graph one can read off the state at time, the coalescent actually at all times, but suppose that we are interested in a particular time q. Okay, so what do? We just keep following the lines, and so at time q we see what happens, how many lines do we have, and so this line is still just pi1. So pi1, there is this line, it's just pi2. This line is pi3. And this line is, in fact, already at this random time. So this will be random time because it depends on the random lines, which are random, as we said, through this initial data and the orderings from this data. So this will be already at this point, there will be a merging. So here, there is a merging of pi4 and pi5. Okay. If this is, say, line psi ordered 5, and therefore here this line represents the whole equivalence class pi4, pi5, And if you had, now I drew only a simple graph with 5 initial states, but you could have 5 initial blocks. You could have n, and n could be large finite number, and so you would have many lines initially. They all start from, so IID, not IID, independent exponentials are all different, so they start completely isolated. So each line starts, and to it is connected just this atom of its own type. It's pi, its index pi I, and then as soon as some lines, so we could have had in here some that interconnect. I didn't draw them. So as soon as 2 lines, an upper line joins or say intersects any lower line, there will be a new merging. So we could have had, for example, in here there could have been a merging before. So this already carries, say, pi. Let's see, this is pi 6 now, and in between there is psi 5. So at this point, we would have, in this case, in this new situation here, we would have a merging of pi 4 and pi 5, and this would carry pi 6, okay? And then at this point, all of the 3 would connect, pi 4, pi 5, and pi 6. So it's very similar to the Kingman coalescent or Moran model, Canning's model, the models from the mathematical population genetics, although it is just similar to that, okay? It is a different model, but it has some of the same properties. That, lines represent partitions, equivalence classes, and then equivalence classes merge together form coarser and coarser partitions. So there is merging, okay. And the point here is that if you, so this is a theorem, a proposition, a lemma, or a theorem, depending, how. But let's just call it a claim. Is that if I were to define a process, pi of q, pi star of q, say, pi star of q is the process, the ordered vector of total masses of equivalence classes at time q. So I'm writing before the claim, this is my process, or the state of my process. At time q, I look at the current partition. This current partition is something. It's a random partition. It has certain equivalence classes. And then to each such class, I say, okay, your mass is x pi 1. Your mass is x pi 2. Your mass is x pi 3. And your mass is x pi 4 plus x pi 5. So the total masses are, I just look at each equivalence class, and I know that to each node there is a mass, its mass. To pi 4 there is x pi 4, to pi 5 there is x pi 5, pi 6 there is x pi 6. So I add up all the masses within a single equivalence class. Once I do this adding, I put them into a vector and I order that vector. So I do this q by q for all q's. I see that this changes at only finitely many points. There's n lines, and they certainly, due to the independent exponentials, there is only one pair of lines that can intersect at any given time. There is no simultaneous intersections. So this is a very, very simple procedure. You could call it a process. If I do this, then the claim is that pi star as a process in Q is multiplicative coalescent, has multiplicative coalescent dynamics, meaning that at any, well, meaning that it really, these blocks, they have masses, and these masses collapse together according to the multiplicative coalescent dynamics. So if I have a block of size x by 4 plus x by 5, it will collapse with this block of size x by 3 at multiplicative rate. Okay, at any, you know, well, okay, so we know what is the multiplicative coalescent, and when you look at this claim and this graph, it is a little bit surprising what is going on, because as we said, okay, the randomness is kind of, it is at the beginning. Okay, so this should not be, I mean, what I want to say, it would not be true if it depends with respect to what filtration. Okay, it's the multiplicative it has the multiplicative coalescent dynamics, but you should not include in the filtration at time 0 the information that you have on size, because if you include the information that you have on size, the rest of the process is deterministic. So in particular, you know that only these two can collapse at any, I mean, you know that only okay, so what's bizarre here is that unlike in the multiplicative coalescent, where any two blocks have a priori equal chance, you know, not equal chance, but for example, these two blocks can collapse, and also these two and these two, I mean, with certain rates. Here we have ordering. So no, I mean, mergings happen 2 by 2, pairwise mergings happen, but only pairs that are close to each other. I mean, they're one line apart, I mean, not even line after line. This corresponds to this line, and this corresponds to the next line, and they have a chance of collapsing before. They must collapse before this can collapse to this. So there is, so this picture is asymmetric. It has some kind of a linear ordering, and by the way, also this picture is well, yeah, there is no, that other picture, the first representation I told you about was only at considering q by q. Okay, so one fixed q, and then there was this auxiliary time s. So in this picture, q was fixed, the coalescent time was fixed, and then it was included here through these rational, well, you divide by q, but then there was another time, auxiliary time s. Well, here we are truly running the coalescent. It seems that we are running the coalescent time q, but only, I mean, something is done initially to this randomness, via this randomness, and only pairs of blocks who are next to each other in this ordering can collapse first, can merge first, and then there will be, once they merge, so then there is just one line, and then another merging can happen, but also this order, yes, this order specifies somehow, it restricts, rather not specify, but it restricts the possibilities, okay? So it is slightly counterintuitive, and I try to understand it, and okay, and I proved it also in my Bernoulli paper, because I thought that I couldn't find the argument for it. I reproved it, or, you know, stated, proved that this is indeed the case, that this, but first I didn't believe it. Okay, so this claim works, and the filtration is, so you should not condition. What you do is you basically, the information that you carry is only the partition structure. Okay, so the right thing to worry about, so at time 0 the partition structure is trivial, you don't know about the size, so, and then you keep discovering, you know, only given the partition structure, you're thinking, okay, so what is my next, when does my next coalescent time come, and what kind of coalescent can I have with what probability? And it turns out that it is like in the multiplicative coalescence. So you just keep uncovering until the first time, and then there is a change in the partition, and you record this change. So you have another partition after the first merging. So two of the blocks, pi something and pi something, collapse, and then you have a new partition, and then again. That's the information that you have, and then you keep going. So, okay.
Vlada, may I ask a question about this coalescence? Look, assume that size 6 and 4 coalesce. Then these blocks have a big mass. Then the speed of coalescence or rate of coalescence with, say, psi1 should be bigger. And your rate is like rate for fourth block, not like for psi4 plus.
Very good, very good, very good. Yes. True. And so
you have to continue the lines that go from above. And
exactly. Yes, exactly. Your intuition is, so this will be compensated by the fact that only the line, so it's the lines from above, how they act on the lines on below. So it turns out that, so that's a very good observation. So there is another, so I was telling you about this ordering that is kind of counterintuitive, but in fact, it is also, it is the how do you so let's try to go a little bit deeper in what you've asked, and yes, so why it is happening with the good rate after merging? Yes, good question. So suppose that unfortunately, this is my line 1. And let's do a simple case. So there is another line and another line. Okay. And your question is that why after this merging of line 2 and line 3 do we have, so at this point there is pi 2 and pi 3 inside of this partition, and this one is pi 1. So why is the I keep the lower rate here, and I mean the lower line. Why then do they merge according to the correct merging mechanism, which would mean that x pi. There is the multiplicative rate. So here, from this time on, this line has mass x pi 2 plus x pi 3, or rather, it corresponds to the partition which has this mass. And this line has, from this time on, x pi 1. Right? And yes. So
I think that it has a shorter time up to coalescence. It starts not from 0, so maybe it can explain why we keep this line. We start not from 0.
No, in fact, it is part of the. Yes, I mean, what is happening is when you look into. So I wrote a proof. I wrote several proofs, but only the last. Like my fourth proof was correct. So I thought that I had a short proof. Then it was a little bit longer. Then a little bit longer, and then finally the correct proof. And I think I have like 4 to 5 pages of argument. And so what's happening here is that basically you have to condition on what's happening. So you look at these coalescing times one by one. Okay, so this is the beginning, and this is the first time, say, something coalesced. And at this time, you have new exponentials. This is an old exponential. This is still psi1. Okay, let's say that this is t1. Okay, time t1 that something happened. So psi1 is the same as psi1 at t1. Okay, it is the same because this line is the same. So, but actually, it turns out in the process of the argument, so you actually need to, I had to actually prove that this process, this partition process, so the process of partitions is a Markov chain, and proving that it is a Markov chain and, you know, getting the correct rates. So what are its rates of changing, okay, transition rates, right? And then an important quantity is this position. So it turns out that this is the position. So if you move your coordinate system so that it starts at this time t1, then you have new lines with new exponentials. So this is what I call everything that stayed from before. I call it, you know, I denote it by t1 psi2. It is the second line which starts, you know, I ignored, or rather I know everything up to here, and now I have the second line that starts from psi order 2 t1, and here's the third line that starts from psi 3 order t1. Okay, it turns out that this random variable is now, it is part of the argument proving the Markov property. It is now truly exponential x pi 2 plus x pi 3. It is no, so before this was exponential psi2, which was exponential with rate x pi 2. This was psi3, which was exponential rate with rate x pi 3. But by the time, you know, if you know that they met at this time, so you know all this information, this didn't do anything, this met with no one, this met, all the other lines didn't meet with anyone, and now this is the first time at which these two lines meet, then you know from this knowledge, you have a new conditional distribution of where the actual lines are. And it turns out that this is still psi1, so it has exponential rate pi 1 distribution. This has a new distribution. It is now an exponential. Given all this information, conditionally on that, it is exponential at rate x pi 2 plus x pi 3. This one did not coalesce with anyone, and therefore, you know, given all the previous information, it's still the exponential with required rate, you know, whatever it is, x pi 4, and all the others. And so this gives you actually Markov property, because then it means that you can continue. Just like the graph continues doing things, but now you know that this starting position is actually exponential with the correct change in the mass. So its rate has conveniently changed, and it is truly the new mass of this block. Sorry, you see what I mean? Was this, are you listening?
Yes.
Yeah. Yeah, so this is quite interesting. I mean, it is, you know, but it takes some maybe it takes some calculations. It takes some pages. So it's a discrete. It is discrete probability. Well, in continuous time, it takes some time to actually work this argument, to tweak it around sufficiently so that it is rigorous. And I didn't find a short way to prove it, but a long way to prove it works, and a longer way than you would think. And it turns out that it works. And so indeed we have this claim, because the lines start behaving, you know, initially you have something, and then after the first transition, the truth transition, something merged, you have the same style of continuing, but this position has the required exponential with the required rate, and so on, and you keep going, and you have the multiplicative well, somehow you need to show that actually this time is the minimum time of n choose 2, well, not n choose 2, but the minimum time of certain exponentials, because you have this configuration and you're waiting for the first thing to happen, and that indeed the fact that pi I and pi j merge is the chance that they merge the first is the multiplicative coalescent chance, and then you keep going, and so it works. So you have this, but here's the point. So I was worried that this is not true. I was somehow worried that this picture is not true before I started proving it. At the first time I looked at it, I said, no way, it cannot be true. And then it took me a year, and not the year that I was thinking about it. The second time I looked, it was a year later, and I said, well, let me try something. And so maybe I finish the talk today with the thing that I tried, something that I knew much better. And it is the picture like this one. So I tried to match this picture, something that I knew about. It was not quite that picture, but the picture from 25 years ago. I tried to match it to this one. And I realized something. I realized that actually these two diagrams can be coupled. So this diagram and this diagram can be coupled. So ZXQ and Uribe's diagram for the same X. So same vector of block masses and Q are naturally coupled. And so you basically use, by using the same size, using the same size and varying Q. So instead of looking at one diagram or one graph, one ZXQ, you actually increase Q. It is now the family of walks. So I call these simultaneous breadth first walks. So it is ZXQ, where Q is so it is a walk in S. So S is its parameter, auxiliary parameter, but also Q is any positive time. Of course, you cannot divide by 0, but so it's like a movie. That's always what I say. It's like a film. So Q is increasing, and the bigger the Q, the closer to the origin all of these points are, and they are also the jump points, and they're also closer to each other. And so these excursions above past minima, they actually change as Q, they merge. When Q is larger, each single jump gets closer to the origin, but they also get closer to each other. And remember, that means that each point gets more and more neighbors. So these are, more and more connections. And when Q is very large, they get so close to the first jump that everybody is connected to the first. This is like the final coalescent. But it turns out that when you look at this, and then when you look at these excursions above past minima, not only do they correspond Q by Q, not only you have a marginal equality in law that connects multiplicative coalescent to the ordered excursion lengths, these excursions above past minima and their lengths, but also as Q varies, you actually get multiplicative coalescent. The way these excursions, when Q increases, the way these excursions merge one onto another. So here's not really a movie, but as Q increases, ZXQ. So for example, you have Q1 And so this is psi1 over q, psi2 over q, psi3 over q, and some other q2 bigger than q1, bigger. So then you have psi1 over q, psi2 over q, psi3 over q. So here the walk would do this, okay, maybe, yeah, something like that. Well, it's already, they already merged, so I jumped too far. Okay, let me change it to another. So maybe this jump is here, and the walk does this and that, and this is too far. Okay, so already the first excursion. So just ignore what I did in black. So in blue. So the first excursion about past minimum is here, and then came the second jump. So the graph would correspond to something like that. Pi1 and Pi2 would merge, and Pi3 would be apart, and maybe some other things would connect to that. But here the time is larger, q2, and we have the same. So this is x pi1. So it is the same thing, but now the first jump is so big. The second jump is like that, and already we see that in the meantime, between Q1 and Q2, they are sufficiently close together that now Pi1 is connected to Pi2, and then there is Pi3 that either connected directly to Pi1 or maybe to Pi2. So they are already joined. So and this keeps going at all times, and I understood something. So there is a link between this graph, the Armendariz or Uribe's diagram, and this excursion process, or rather a family of excursion processes. And it turns out that if you look at this ZXQ, okay, so I don't know if I should keep going or maybe stop here, but I sort of feel that, if I don't say, then you will ask me what is the what is the link. It turns out, okay, so let's so I prefer to sometimes, Vitaly knows that I prefer to draw these triangles. So this is so it's reflected ZXQ. So by reflected, I mean reflected above past infimum. So initially, when Q is small positive number, of course, all the psi I over Q are far away from each other. So psi 1 over Q is much smaller than psi2 over q, much smaller. So they are all apart. Okay, so all the excursions are basically triangles with this side is x pi 1, this side is x pi 1, this side is x pi 2, x pi 2, x pi 3, x pi 3. See, so psi2 over q, and so this is some small q small, and then these triangles keep going as q is increasing. They keep going towards the origin, and they are approaching each other. And then there will be the first time, some random time, let's call it then q1, random time, when one pair of these triangles, which there will be the first triangle q, some psi I plus 1 over q1, which will just, how do you say that? When you are running after someone, you just catch them. It will just catch the one before it, psi 1 over q1. Okay, there will be some initial time q1. Before that time, so it's a random time. Before that time, all the triangles are separated, And at that time, there will be a pair of triangles, say one is bigger than the other, and here's the time, on this S scale, auxiliary time scale, this is psi I over Q1. This is the point, of course, psi I plus over Q1 plus x pi I. And it is the same point as psi I plus 1 over Q1. And this point is, of course, this point is psi I plus 1 over Q1 plus x pi I plus 1. This is the coming from the first definitions that we did, okay? So this is the zoom of what's happening here. So there is this first time, random time at which two of the triangles meet, and right after Q1, the excursion will be already, you will have, how do you say that, you will have a merging in the corresponding coalescent, where here you have Q pi, x pi 1, I, and here you have x pi I plus 1, and they will have an edge between them. So immediately at any positive, small positive epsilon after time Q1. And the others are still apart, okay? We cannot assume, these are independent exponentials. The others will be still apart. So they will be just the time of this merging is Q1. And so here, look at this equation. And then just note that I wrote nothing else, but if I put everything together, it is like I wrote that the line, it is the same, it is equivalent to be writing that the line y equals x I plus 1 minus q x pi 1 plus x pi 2 plus x pi I, and y equals x psi I minus q times x pi 1 plus x pi 2 plus x pi I minus 1. These two lines intersect at time q equals q1. These two lines are actually lines from Uribe's diagram. They are lines from here. They're the I and the I plus first line, and this identity that these two triangles, this one catches up with this one, is when you look at it, it's this identity between lines. If these two lines are the same, at time q, it is the same point. It just means that this minus that is the same, and it is precisely this algebraic expression. I assure you, it is the one. So then I realized, let me close the window. Then I realized it is the same. Actually, it is the same condition in something that I knew would be true. Could be true. And what Armendariz or Uribe claimed that it was true, and then I started believing because before I didn't. Okay, and so maybe this is a good time to stop. Sorry for bothering you. Last time it was very few technical details, and this time it was kind of a lot. To some extent, a lot of details, but I hope it was still interesting, and maybe next time then I can tell where does the immigration come in. Okay.
Thank you very much. And actually, we are waiting for connection between these pictures for one process. And it was my question also about the space-time distribution of those meeting points in Uribe's diagram, and maybe this is an explanation of it. Thank you very much. And maybe somebody have questions. Okay, if there are no other questions, then I think that we will be interested in the continuation of your talk.
Yes, okay.
Because
after pause. Yeah.
Okay, maybe next semester, because it seems that maybe the same construction can be related much more complicated set of random variables than just this simple, as you said, simple, very simple Levipos. But for me, this set of exponential random variables can be treated as a very simple point process on the line. Maybe if you take a much more complicated process, then you will get another picture and much more rich structure. So, I think that it is a very interesting subject, and hope to hear you again at our seminar.
Well, thank you very much, and that's a very kind, very kind of you to say that you're enthusiastic, and I would be happy to explain more. I mean, so the thing that, you know, why I mentioned immigration initially, and I was very ambitious that I would do everything in one talk, and I could probably if I were running 3 times as fast through the material, is that, you know, so at least there is, so this is very interesting that you can bring in immigration. Interesting for me, say. You can bring in immigration into the multiplicative coalescent dynamics, and the picture that I told you today with Uribe's diagram and the corresponding simultaneous breadth first walks holds. I mean, it remains true, except, as you say, this is a very simple point process that we had in Uribe's diagram on the ordinata, very simple point process. And now the point process that you have with the immigration picture changes, and it becomes way more complicated, but some results are known. And it is the process that I've been asking people about for a while, and nobody's told me yet that they saw anything like it. But it would be very, I think it's a very interesting process, and, you know, unfortunately, so about things that I wrote, about things that I spoke so far, I have written documents, papers published or preprints, and both preprints and preprints never become papers and papers. But on the immigration, it's still work in progress, and I'm hoping to finish something. But even if I do not, by the time I come next time and speak in the seminar, you will see that it is a much more complicated structure, and it's worth investigating. And it could be investigated from more. From more, you know, from more angles. For example, you are interested to change the process, and I'm interested, for example, to bring in more into the dynamics and see what kind of changes happen to the process. So I agree that, yeah, so I'm glad that I presented this rather than some other technical thing, and
okay.
Thank you very much.
Okay, thank you. And last, what I have to say today, that next time we will have a special session of our seminar for, we call it Skorokhod readings, and we will have 6 speakers. They will be young people who are doing the diploma of or magister thesis from different countries, and they will have short talks like 25 minutes each. So please come in and see what young people can do next week.
Andrei Anatolyevich, and the start of seminar will be not 5 o'clock, but earlier.
Yes,
This is
yes,
important.
and you will get an announcement. Yeah.
Okay,
Yes.
thank you. Mhm.
Okay.